Welcome back to the podcast, everyone. Today I'm joined by Fran Chadha-Day, a theoretical particle physicist who discovers new fundamental physics with astrophysical observations. So, Fran, that's quite like an interesting juxtaposition. Could you tell us about how the astrophysical observations you look at relate to particle physics?
Yeah, so space and astrophysics is actually a really great place to look for particle physics, because in astrophysical systems like stars and galaxies, we have access to conditions that we could never reproduce in the lab. So we can have very high energies, very high magnetic fields, very large distances that would be simply impossible to recreate on Earth. And these extreme conditions allow us to probe the laws of physics in completely different regimes than what would usually be possible in a lab. So looking at telescope observations, looking to see if there are any kind of anomalies or interesting effects that could be explained by new particle physics is a really important complement to things like particle colliders and lab experiments.
Okay, so when you say like you're looking for new kinds of physics, is that to do with like things like dark matter?
Yeah, so dark matter would be one big one. So dark matter is matter that we know exists because we can see its gravitational pull on other matter, but we can't see it in any other way. So we don't know what it is, and most physicists think that dark matter can't be explained by any of the particles that we already know about. So really by new particle physics, we mostly mean just new particles. And we hope that one of these new particles would make up the dark matter. Okay.
So, other than dark matter, is there anything specific that you're looking for? Or...
Yeah, so I mainly work on particles called axions, which could be the dark matter, but they're also motivated as a generic prediction of string theory models. So string theory is probably our leading theory that combines both quantum mechanics and gravity, and it tries to explain all of the particles we know about as different modes of vibrations on strings, which would then be the fundamental objects. String theory is unfortunately kind of light on experimental predictions, but the existence of a large number of light particles called axions is one of the predictions of string theory. These axions can act as dark matter or as dark energy, which explains the accelerating expansion of the universe. And they can also provide a solution to what we call the strong CP problem, which is basically why does the neutron not have a measured electric dipole moment, whereas in the standard model, our best theory of particle physics, we would expect an electric dipole moment for the neutron. So that's quite a specific technical problem, but one that physicists have been working on for a long time.
That's cool. I hadn't heard about this CP problem before. Axions sound quite grand, anything more complicated than the electrons, and I start scratching my head a little bit.
Well, in many ways, axions are simpler than electrons, because
really?
Axions are bosons, which means that they're kind of like the kinds of particles that carry forces, so like photons, like the Higgs boson, whereas electrons are fermions, which means they're matter particles. And notably, fermions have to obey the Pauli exclusion principle, which basically says that there can be only one particle per kind of quantum state. So this is why you get these electron shells in atoms. But implementing that in quantum field theory is much more complicated mathematically than working with bosons. So yeah, in many ways, axions are the easier option. They can actually often be described as using classical field theory.
Okay.
Possibly that's like slightly advanced. I don't know.
Yeah, you know, you really have to use classical field theory.
I don't know, whether your audience is mainly kind of physics undergraduates or just more broad.
At the moment, it's not really much of anybody. Wow. Okay. So, what kind of observations have you seen recently, then, if any, in doing your research?
So, I mean, okay, we should get one thing straight, which is there is, axions might or might not exist. We're still very much at that stage. There are some kind of hints where people say they might exist. For example, there is some suggestion that some stars are cooling faster than we would expect. And if axions exist, then they would provide an additional cooling channel via the star emitting axions. But in general, they may or may not exist. So my work focuses mainly on X-ray observations and radio observations. So occasionally I get to do some actual X-ray analysis, but to be honest, it's mostly like maths on pieces of paper type thing.
Of course, so more theoretical stuff.
Yeah, definitely.
Okay, so how does theoretical analysis help in this kind of thing? I guess the picture that comes to mind is a bunch of people staring in their telescope looking for stuff.
Yeah, so my research is really working out if axions exist, what would we expect to see in the telescope? So, we're really trying to compare observations with the predictions of different models, but working out those predictions can be quite mathematically involved.
Okay. How, mathematically involved? What kinds of maths do you have to use?
Oh, gosh. Well, I guess in my current work, I'm using thermal field theory. So, where should we start? So, quantum field theory describes the behaviour of quantum particles that can be relativistic. And the way you do that is by describing the particles as excitations of a field. So a field is just something that kind of assigns a value to every point in space and time. And the particle is the excitation of the field. What makes it quantum is that the field itself is quantized. So it's a quantum operator. It has kind of commutation relations like in quantum mechanics. Now, kind of standard quantum field theory is done at 0 temperature, whereas thermal field theory is quantum field theory, plus you can have a non-zero temperature, you can have a kind of background thermal bath.
So I guess that's probably more realistic then.
Yeah, it is certainly more realistic. So quantum field theory tends to be applicable at something like the Large Hadron Collider, where, okay, you're not at 0 temperature, but you're in a very, very controlled environment. There's not this surrounding bath of other stuff. You just have your 2 protons that you're colliding. Whereas thermal field theory needs to be used in, environments where you've got a background plasma or something like that.
Okay. So do you have any sort of ideas what the future of your research might hold, or is it kind of a grey area at the moment?
Yeah, I think at the moment it's relatively grey.
That's exciting though, at least.
Yeah. So there's kind of a number of directions that I could go in. So at the moment I'm thinking a lot about superradiance, which is a process where if you have a rotating black hole or star, you can actually have a build-up of particles around it. And they kind of steal the star's rotational energy to create more and more particles. So I'm trying to look at the conditions where that can happen. And then the other thing that I'm thinking about, which is quite different, is that we recently launched, I say we, I wasn't involved at all, scientists recently launched IXPE, which is a polarizing X-ray telescope, meaning that it can measure the polarization of X-rays from sources in space rather than just the flux. And so I'm thinking about, with all this new data, including polarization, what could be done for particle physics.
Okay. do you have any idea what can be done?
So the main way that people search for axions, well, one of the main ways, is that in the presence of a background magnetic field, axions and photons can interconvert, so they can turn into each other. So this leads to all kinds of interesting signatures. But the conversion actually depends on the polarization of the photon. So the existence of an axion could actually kind of change the polarization of different stars. So that would be one thing we could look at, for example.
What do you mean by like polarization in this context? Because what comes to my mind is just, light or something that's only allowed to oscillate one way.
Yeah, that's exactly what it is. So if you imagine a beam of light, you can have one that's fully polarized in the x direction, for example, and that means its electric field is oscillating in the x direction. Whereas if you have one that's kind of mixed, maybe you have some that are polarized in the x direction and some that are polarized in the y direction, then depending on the direction of the magnetic field, some of those photons are going to convert into axions more than the other photons. So then in that scenario, the kind of polarization fraction of the beam would actually change because of the interaction with axions.
Okay. How do you this might be a bit of a tangent, but how do you reconcile that idea of polarization, like the waves, with also the idea that the light's particles, like photons?
Oh yeah. I mean, that's kind of an interesting question. So yeah, you can certainly describe like an individual photon will have a polarization. It's described by a different polarization vector in quantum field theory. I guess it's just the same basic thing as wave-particle duality, that when you have a photon, there is an electric field associated with that photon, even though the photon is a discrete chunk. I think it's just the same thing as wave-particle duality, with electrons when you have the double slit experiment and kind of everything.
Right. I feel like coming to uni, now we kind of have to take wave-particle duality and stuff for granted to do things like quantum mechanics, but it's still quite disturbing. I think people push over that.
I guess I'm kind of used to it. I mean, I guess we're getting a bit philosophical here, but I guess my own view is that we see Newtonian mechanics as kind of nice and normal and intuitive, and quantum mechanical effects as weird. But personally, I think that's just because we're used to Newtonian mechanics in day-to-day life, whereas, macroscopic objects that we interact with don't behave quantum mechanically. So I think it's just to do with what you're used to. And I'm now quite used to quantum mechanics, so I just stopped finding it weird.
Yeah. Maybe in another universe for really small people who live with quantum mechanics and they think Newtonian stuff is weird.
Yeah.
So how did you get into this kind of research then?
So I think I wanted to do physics for quite a long time. I just always thought physics was really cool. And then after my third year of undergrad, I did the summer student programme at CERN, which I think is still running, so I'd really recommend that as an experience. And that was really good. So they have a lecture programme where you learn all about particle physics, and then you do a sort of little project to do with, what they're doing at the moment at CERN. So that was really fun, and that really made me realise that what I wanted to do was particle physics.
That's neat. That does sound cool. I'll have to, keep that in mind when I graduate.
Yeah.
A lot of the people I ask, it seems that they do some kind of internship or something like that, and then that introduces them to a field of research, and then that's how they get into it. I'm trying to find internships right now, but it's very hard.
Yeah, I mean, I think the pandemic has really kind of slowed that stuff down.
That's a shame. But hopefully it'll be easier within 2 years.
Yeah.
So why would you say your research is important to, a layperson?
Well, okay, I'll be honest. I don't think my research is going to have technological applications in the near future. However, I think, what I'm doing is contributing in some very small way to uncovering more about the fundamental laws that govern the universe and how everything around us behaves. So I think doing that is really always going to be progress, both for our understanding of the universe and for our ability to build technologies that will do useful things.
Yeah, like a lot of it seems like a lot of things when they're sort of, I don't know, discovered, like we don't really have many applications, but then later, like applications are found.
Yeah.
So.
Yeah, and I also think it's something that people just want to know. Like, I think it's quite intrinsically human to just, like, want to know how things around us work. I don't think it's, like, only physicists that want to know that. I think lots of people just enjoy learning about it, even if they're not doing it themselves. I feel the same way about something like history. Like, you might think studying really ancient civilizations, for example, doesn't have a direct application to, you know, humanity today. I suppose you could argue it's learning more about human nature, but also, like, I just want to know. I think it's, you know, just really natural to want to know about the history of humanity. So I'm glad people are working on that.
Yeah, that's an underrated reason, I think.
Yeah.
Okay. So you also do like work as a scientific comedian, right? Could you talk a bit about how you got into doing that?
Yeah, so I started during my PhD. So I did a set with an organisation called Bright Club that kind of facilitates academics to do stand-up about their research. And I think it was just on a bit of a whim, like we got an email around the department saying like, oh, would anyone like to do this? And I thought, well, this sounds cool, I'll do that. So I did that once, and then it just sort of went from there. So then I think someone saw me and emailed me to ask if I wanted to do another event they were running. And then, I don't know, it just kind of snowballed.
Okay, so would you say you do it mainly just for fun, or do you have like, you know, grand outreach like plans?
I mean, mainly it's for fun, I'll be honest. I do think it's a really cool way of doing outreach, an important addition to the kind of, you know, tapestry of outreach that we offer, because it is something that is meant to be just like primarily entertaining and fun. I think the kind of more, you know, standard science talks are really good too. But, you know, for some people, they might just feel a bit like school or a bit too much like work, and they wouldn't be appealing. So if you can do something where it's like primarily aimed at like making people laugh and being enjoyable, and then it also has some cool science in, I think that's also a great method of public engagement.
Yeah, that's cool. If you have like anything you want to talk or like mention specifically, then feel free to like mention it.
Yeah. Oh, what else? Oh, and science comedy. I will hopefully be doing a show at Durham Fringe, and just, you know, just use your podcast to plug that. Yeah, I imagine the audience will be like Durham centric. So that is called Our Dreams Made of Atoms. And, you know, all being well, that'll be in the Durham Fringe programme. But the programme hasn't been officially released yet, so that's why I'm putting in these kind of, you know, hedging words. But yeah, so that'll be about physics and about my experience of physics as a way to understand the world. And that is, yeah, my first solo show since before the pandemic, so we will see how that goes.
Can you give us a sneak peek? You know, how do you think physics like informs how we see the world?
Yeah, so I think physics is a really powerful way of looking at the world, and one thing that just like always astonishes me is like the extent to which it works. Like, you know, I think it's not obvious that we should be able to use mathematics to, you know, predict experimental results to like, you know, 10 digits of precision at this point. I think that's really cool, and I think, you know, that's telling us something about the way the universe is put together. And and perhaps something about mathematics. I've always found it weird that, you know, mathematics is essentially something that humans made up, as far as I can tell, but then it actually seems to, like, very much correspond to how the universe operates as well.
I'd be really interested if we, like, this is going to sound really out, if we, like, find aliens or something,
Yeah.
like, would they have mathematics? Would it look different to ours? Because,
Yeah.
like, the way we use it for modelling is, like, really good. Yeah. Like, how different could it look and still be as good, if that makes sense?
Yeah, that is quite interesting. Yeah, like, I think obviously it would look quite different, because there's lots of things in mathematics that we know are just conventions, and there are things you could do differently. But yeah, maybe there's some entirely other system that would also work.
Yeah. It's like, you know, do you say about humans have invented mathematics, or have we discovered it, you know? Is it like something inherent about the world?
I just don't know. I'm not going to provide answers in the show.
It's okay. So do you have any particular hopes for the future of your research?
Well, I guess my, like, big long-term hope is that we discover what dark matter is in my lifetime, which I don't think is implausible. You know, there's lots of dark matter detectors operating at the moment, which, you know, could return a signal. We just don't know. I mean, for all I know, it'll be announced tomorrow.
That'd be good.
But it's just, you know, it's just one of those things. Unlike, say, the discovery of the Higgs boson, we really don't have a sense of what we expect dark matter to be, what we expect its interactions with regular matter to be. So there's just no way to predict. All we can do is kind of keep looking in as many places as possible.
Okay, so if you had to, like, I don't know, make bets, what do you think's the most, like, likely explanation for dark matter?
Oh gosh. Yeah, it's very hard to say. I actually think the most likely explanation is that dark matter is more than just one thing. So we know that regular matter, which makes up 5% of the universe, that's 18 different kinds of fundamental particle. So, you know, we kind of know that the universe isn't straightforward. It's not, like, simple. So I think actually possibly there's, like, several different particles that are as yet undiscovered and which are making up the dark matter. If I had to choose just one, which I think, like, even though it's not what I work on, I think my bet would be sterile neutrinos. Which are, so, you know, there are, one of the particles in the standard model is the neutrino. Well, there's 3 kinds of neutrino, actually. And they're very, very light. So they're very weakly interacting, but they're very light, too light to be dark matter. However, it is very straightforward to write down some extra neutrinos, which would be even more weakly interacting with the standard model, and would be much heavier. And they would give mass to the neutrinos, which is something that we need. And they would also be a very easy dark matter candidate. So I think sterile neutrinos is where I would place my bet. But I mean, obviously I don't know.
Anything else you want to bring up?
No, I think that's all my thoughts.
Okay. If you want to, you know, take one last time to plug your shows and whatnot,
yeah,
and
okay.
you can wrap up.
Well, when the Durham Fringe programme comes out, check. Our Dreams Made of Atoms. It'll run for 3 days in the Cathedral Cafe, hopefully. I don't remember which 3 days it is off the top of my head, but, you know, you'll be able to look that up.
Maybe I'll see if I could put it in the show description or something.
Yeah. Yeah, hopefully the programme will come out soon and then people will actually be able to see it.
Is there anywhere online people can find you, like on Twitter or a website?
Oh yeah, so on Twitter I'm at Fran Chadha-Day and my website is physicsfran.com. I actually want Physics Fran on Twitter, but someone else has it. They have like 2 followers and 1 tweet and no profile picture. No. It's very irritating. There's no way to get in touch with them, seeing as clearly they don't check their Twitter.
Disaster, damn. Maybe you can do some research on how to track them down.
I don't care about it that much.
Damn, okay. Thank you very much for coming to speak to me. I'll see you guys on the next episode. Bye.
Bye.